This is Daniel Coosbury, and in this lecture we're going to look at compound interest. So the biggest difference in this compound interest as compared to simple interest, what we looked at in the last lecture, is that simple interest, pretty much you imagine sticking your money into some account and it's going to accumulate interest at a consistent rate over a certain amount of time, and that rate of accumulation is not going to change in simple interest. Where in compound interest, what's going to happen is that money and the interest included is going to compound over a certain number of times each year, and as time goes on, you're not only going to be earning interest off of the original money that you put in the account, but also over like whatever the present amount in the account is at the time of the compounding period. So if you put money into an account and then a year later it compounds, it's going to look at that new set of the new value of the account with the interest included as that's kind of the new amount we're going to start accumulating interest on. So it's pretty nice. It's a pretty nice way to make money, and mathematically we're going to have to look in a different formula to do compound interest, and so it's going to get a little more complicated, but I think it's going to be doable. So first, here's a compound interest formula when the interest is compounded once a year. So we're not worried about compounding any more than one time every single year. So this is the formula we're going to do. We have A is going to be the future value of the investment. P is the present value, or the amount that you put in originally. R is the interest rate, and T is the amount of years that the money's sitting in that account for. So here's an example where we deposit $4,500 to a saving account with an interest rate of 5.5%. A says find the amount of money in the account after 3 years, subject to interest compounded once a year. So this compounding once a year thing means we can use this formula here, and we want to find A, and we can just start plugging in numbers that we know of. For example, we know how much money we put in the account to begin with. We know what the interest rate is, so that's going to be R, this 5.5%. Remember, I got to convert that percent to a decimal, so 0.055%. And then I'm going to raise that to the T power. T is going to be the number of years, this 3 right here. So I can do all that in my calculator and just type that in exactly as you see it, parentheses and all, and I end up getting this value here as my dollar amount. So this is how much money is going to be in the account after 3 years. And I'll round that to maybe 2 decimals so you can see like cents there. I don't really care about 3 or 4 decimal places out there. So that's a lot of money at that interest rate with the compounding. Like the amount of money I put in increased by over $700 in 3 years, which is pretty nice. So part B says let's find the interest. Well, the interest is how much money you made over the course of time. So we can take that 528.409 and subtract the original value. That's not a big deal. Not a hard thing to find. And when I do that, I get $784.09 as my interest. So you're going to see in a lot of these examples, compound interest is a much nicer way of making money if we can afford to do it. So what's going to happen oftentimes is you're not necessarily going to compound interest once a year. It might happen several times a year, which is going to be more beneficial to you. And so here's a more general formula for compound interest where we're going to introduce a new variable, N. So N is the number of times in 1 year that the interest gets compounded. So if it gets compounded semi-annually, we would say that's twice a year. Or if it gets compounded monthly, that would be 12 times a year. And so N's going to change based on how often it gets compounded. So let's look at this next example. We deposit $7,500 into a savings account. That's going to be our P. We just know that already. And the account has an interest rate of 5%. That's going to be our R. The interest is compounded quarterly, so this means that it's going to be compounded 4 times a year. So once a quarter, 4 times a year. And with those 3 numbers, I believe I can calculate my future value pretty easily. So I'll use my formula just like last time. So P goes there, and then I'll do 1 plus R, which is 0.05, over N, which is 4, and then raise that to the N times T power, or the 4 times, what was T? 7. We didn't find T's right here. How much money will you have after 7 years? So I can do all that in my calculator. And you want to be careful kind of punching this in. Make sure your order of operations work out. The only issue putting this in the calculator is you might want to check and make sure that both of these numbers end up in the exponent. So you could put them in parentheses, maybe 4 times 7 in parentheses, and I end up with 10,619.94 dollars. So that's not too terrible. So the tricky thing with this formula is just making sure it gets typed well. But otherwise, we're just plugging in different parts, pieces of information to this formula. Some of the interest I got when I did that subtraction, the future value minus the present value, is this. So in 7 years, I made over $3,000, which is pretty nice. And so that obviously I invested more here. It's in the money in the bank for a longer amount of time, but also I'm compounding my interest 4 times a year instead of once a year, which also made a difference, and I made a lot of money with that investment. Okay, so there's another idea that we're going to call continuous compounding, and that's when we are not really interested in compounding a certain number of times each year, but the idea is that like maybe even more than every single day, the interest is getting compounded basically all the time. And so when we don't have a particular compounding period, but it's getting compounded all the time, just whatever, we'll call that continuous compounding. And notice we have a new formula for that down here where there's no n because we don't have a certain number of compounding periods. We can't put a number in it. So it's just going to be continuous. It's going to keep on happening. So we still have a present value, the interest rate, and the time, but we just don't have that in anymore. And now we have the number e in here, which is in your calculator. That's the number 2.71 and some change. And so we'll raise e to the r times t power, and that's just some nice formula that someone came up with to do continuous compounding. So let's look at this example. You decide to invest $5,000 for 6 years, and you're allowed to choose between 2 accounts. The first account pays 6% interest, compounded monthly. That's going to be important. The second account pays 5.75% interest, compounded continuously. And the question is, which is the better investment? You might rephrase this question, what investment is going to make me the most money if I invest $5,000 for 6 years? So we're going to use both these formulas and see which one the better investment was. Okay, I'll start with the compound interest formula with the number of compounding periods. So I'll put my p there, and I'll do 1 plus r over t. So that first option with the 6% interest, I was compounding monthly, so my n is going to be 12. 12 times 6. We'll go up here. So I'm using this first formula down here for number 1. So give me a second. I'll do that in my calculator. And again, you just want to make sure that when you punch all this stuff in, namely these exponents here, you might want to put parentheses around them when you put them in the calculator. Put a little caret sign and then parentheses, and then your order of operations should work pretty well. You've done something wrong when you do all this stuff and you end up with like $10 billion or some number that's way off. It's way too big. So what I got 7,160.22 for that first account. So I made a decent amount of interest. The question is, what about if I compound continuously? Is that going to give me more or less money? So I will use the second formula now. My future value is equal to the present value times e to the r times t, so to the 0.0575. It's a different interest rate in the second one. Change that to a decimal. And then multiply that times the number of years I'm investing, which is 6. So I'll do this in the calculator too. The e is in the calculator. You look for the, if you do second log, you have the e to the power thing. And yeah, just make sure that these two numbers are multiplied in parentheses in your calculator so that the order of operations will work out well. 0.0575 times 6. And I end up with $7,000 $59.95. So there's the dollar figure if I invest in the second account. So at this point, this question is really easy to answer. Which is the better investment? Well, if I do option 1, I'll have this much money at the end of 6 years. If I do option 2, I'll have this much money at the end of 6 years. So I'm going to go with option 1 because the output is bigger, the interest I earn is bigger. So I'm going to say this is a better choice and call it a day. So there we go. So just like with a simple value formula, we can use the formula to find out other pieces. So there's 4 different pieces of information that you put in. If you know, well, actually there's 5 in this case if you count the future value. So if you have the present value, the future value, the rate, the compounding periods, and the amount of years that you invest for. So with the 5 pieces of information, usually you only have 4 of them. So like in this example, we have 4 pieces. We have the P, the R, and the N, and the T, which means we could find out what A is. But if we needed to find out some other part of it, if we have 4 different numbers, for example, maybe we need to solve for P, then all we need is the future value or the desired future value and all the other information, and we can solve for P, which is how much money we want to put in. So this is a practical example. How much money should be deposited today? There's that present value. Into an account paying 5.5% interest, compounded semi-annually, so that it will accumulate to $25,000 in 6 years. So do you see the pieces I have? I see T is there. My future value is there. I want it to be that value in 6 years. Semi-annually, that's going to be N is equal to 2. And there's my interest rate, where it's going to be that as a decimal. Okay, so what I can do is I can plug all these things in now and solve for P, which this formula went ahead and solved for P for you. So you can just put P on the left-hand side and plug everything else in. So this is 25,000. This is 1 plus 0.055 over 2. All that goes in parentheses times 2 times 6. And in your calculator, maybe put that in parentheses too. So you want to be extra careful putting this one in. I would say go ahead and put the entire denominator in parentheses and maybe another parentheses around the exponent too. And when I do that, I get $18,053.36, which is pretty reasonable. It's a reasonable number. It's not really, really small. It's not like 5, and it's not like huge. So it looks pretty good. So the answer to the question is if I invest a little over $18,000 into this account that compounds semi-annually, paying 5.5% interest over 6 years, I end up with my desired $25,000. So this compound interest formula is useful for solving for other things, and we're just fortunate enough to have a formula with P by itself already. So all you got to do is plug things in that you know, and it'll spit out P. We have another concept that we'll talk about now that we have a different kinds of earning interest. We talked about simple interest and compound interest. This is going to be the effective annual yield, or it's also called the effective rate, is the simple interest rate that produces the same amount of money in an account at the end of 1 year as when the account is subject to compound interest at a stated rate. In other words, if we put money into an account that's earning interest and it's compounded a certain number of years, we can find that interest. I can tell you what the amount of interest you earn using this formula. It's just how much the money grew by. The effective rate is basically what kind of simple interest rate would we have needed in order to get that same amount of actual interest. So that might make more sense when we do this example. So here's a example. We're going to deposit $3,500 into an account paying 8.5% interest compounded monthly. So if I want to find the future value after 1 year, I'm going to use my compound interest formula. Since it says it's compounded, 1 plus R over T, which is 1. No, wait, it's R over N. R over N times N, or to the N times T power. So that's where the 1 comes in. So we're compounded monthly, N is going to be 12. And I'll just do this real quick in my calculator. And I end up with $3,809.37. So that's how much money I'm going to have after a year. And then the question then is, use the future value formula to find for simple interest to determine the effective annual yield rate. So what? So here's kind of what we've done. This is how much money I put into the account, or I want to put into the account. This is how much money I would have after a year of investment into this account. And if I were to take these two values, so this is my future value, this is my present value, and if I were to plug these into this simple interest formula, I'll be able to calculate, well, if I just plug this into a simple, and if I just invested this using simple interest rather than compound interest, I'll be able to figure out that rate, which is the effective rate, or the effective annual yield. So in other words, just imagine that all the money I earned from this compound interest experience, what would be the interest rate using simple interest? Anyway, here's what I'm going to do. I'm going to plug those things into the formula. I'm going to put A right here. 09.37 is equal to 3,500 times 1 plus R times T, which is also 1. So you see, I don't know what the simple interest rate is. I know what this compound interest rate is, but I want to know the simple interest rate, which is also called the effective annual yield. So that's going to be this number when I get done, this R. Okay, so I need to get R by itself. So maybe I can distribute this on the right. I get 3,500 plus 3,500 R. And here, this just comes down. Just doing some algebra here now. This isn't going to be too bad. So then I'll subtract 3,500 from both sides. And I end up with 309.37 on the left-hand side and 3,500 R over on the right-hand side. Do the division, divide by 3,500. And I need some more space. Then I end up with R is equal to 0.0884, and I'll just kind of stop it there. So my effective annual yield in this case is going to be, well, it's actually going to be, hold on, it's going to be 8.84%. So here's kind of what I've done is I've considered this situation where I've got an option of investing into an account that pays 8.5% interest. It's compounded monthly, and I want to consider how that investment and the interest I earn off of it compares. I might want to compare it to a simple interest situation, and if I were to invest that same money using simple interest for a year, the actual rate I would need to get the same amount would be this. So we'll call it the effective rate using simple interest. It's a little bit higher than this 8.5% up here, which makes sense because the compounding is going to increase the amount of interest that we earn. So that's something we can do. And so what we used to do that was we used the simple interest formula, and then we used the present value and the future value from our compound interest, and then we just solved for R. We knew what T was. So this is another case where we have this formula. We have 1, 2, 3 pieces of information. We're solving for the fourth using algebra. All right, so one nice thing, if you didn't like that, one nice thing is there's a formula for calculating the effective annual yield. And we're going to start calling that effective annual yield Y. And so basically, if we know the number of compounding periods and we know the investment rate, or the interest rate, sorry, then we can calculate the yield without doing what we did on the last slide. But we can do stuff on the last slide too. All we did was use a little bit of algebra. But now we got this formula that's going to help us out. So here you have an option of investing into an account that has a nominal rate of 4% compounded daily. And it says find the account's effective annual yield. So we're going to go ahead and do that. If it's compounded daily, just theoretically speaking, we can, well, let's put the rate up here. We could just think of N as being 365. Sometimes you'll see that 365 change a little bit for various reasons. For example, maybe doesn't earn anything over certain holidays or things like that. But anyway, we'll just use 365 to be theoretical. And so this is just our formula, and it's going to spit us out some sort of rate. It's going to be a decimal too, and I should be able to do all that in my calculator if you use those parentheses the way they're written. And I get 0.0408, which is also 4.08%. So there's my effective annual yield if I use this and I compound it daily. So that's just a little bit higher than this 4%, but it is higher, which is important. So again, if you didn't like that last example where we did the algebra, we have a nice formula here that'll calculate the same thing. So that's pretty much what you need to know about compound interest. There's a lot of different formulas now, but the good thing is if you all you really need to know to use any of these formulas is all but one piece of information. So here I had 1, 2, 3 pieces of information. I just needed 2 to be able to use it, and things worked out pretty well.